Hello everyone, I'm Suraj Kothari. Welcome to the second segment of my talk. In the last segment, I discussed execution behaviors and their exponentiality. We looked at examples where one must examine all behaviors to verify software vulnerability. We looked at truth table as a way to represent execution behaviors. The 2007 Turing Award was given for model checking for hardware and software verification. Model checkers use binary decision diagram for compact representation of execution behaviors. Binary decision diagram can fail to produce compact representation as we illustrated in the DBZ example. We looked at two other examples that present loop behaviors and unstructuredness as other issues for representing behaviors using truth table or decision diagram. Besides compact storage, we need a representation that enables analysis of all behaviors without excessive computation. With zillions of behaviors, it is intractable to enumerate every behavior and examine. Now, we shall discover algebra that enables compact representation and accurate analysis of all behaviors without enumerating them. We want to make it simple to go from program statements to execution behaviors. We conducted several experiments over the last 15 years to find a good solution to manage the complexity of execution behaviors. We built the Atlas platform as the apparatus for conducting our experiments. In 2015, we had a breakthrough with the verification of Linux kernel that hinted at mathematics as the way to manage the complexity of execution behaviors. Continued experiments over the last 5 years led us to the discovery of algebra. This is how the algebraic method would work. From program statements, we set up a system of linear equations. We solve the equations and get CRS, compact representation with successor elements. We will discuss what successor elements are. We map CRS to CRB. From CRB, we get execution behaviors. So there are really two major steps. One from program semantics to algebra that gets us CRS. The second step is from algebra to program semantics that gives us execution behaviors. Now let's refresh our memory from school days. What do we need to set up a system of equations? We need variables, addition, multiplication. What else? Here is a problem from school days. The problem is about campsites and campers. It requires us to find the number of campers at each campsite. So we set up the equations. We get 5 equations in 8 unknowns. That could mean infinitely many solutions. However, that will not happen in this problem. The problem has an additional constraint. We are finding campers at each campsite, which means the solution must be a non-negative integer. So solving the system of linear equations has a long history. Aryabhat, the Indian mathematician, wrote a book called Aryabhatiya. Here is a stanza from his book. They used to write mathematics as poetry. This stanza 12 from Ganita, which is a Sanskrit word for mathematics, one can see that it is really about solving linear equations. From Aryabhat we come to Gauss, who came up with Gauss elimination. Later, Jordan did a variant of Gauss's method and we call it Gauss-Jordan elimination. The Gauss-Jordan elimination has a back substitution, and we substitute one equation into another so that we can reduce the size of the equation. In this case, we get a reduced equation d plus e is equal to 4, and we continue this until we get solution for each variable. Linear equations enable mathematical modeling in other branches of science and engineering. Can we represent execution behaviors compactly with algebra and derive the representation by solving linear equations? That has been a question on my mind for quite some time. What is algebra? Algebra has elements. Then algebra has operations over those elements, and those operations have properties. In school, we typically deal with algebra where the elements are numbers, but they don't have to be numbers. And that takes us to a quote by Kronecker. Kronecker says God made integers. All else is the work of man. So what do we need to create for algebra that would work for software? When Kronecker says all else is the work of man, in my mind he's talking about the work of his friends Dedekind and Kumar. According to Kronecker, God created integers. His friend Dedekind created an algebraic structure that now we call algebraic ring. Why did he create the ring? To prove a theorem about God's creation. It is Fermat's last theorem. Fermat stated his theorem in 1637. In integers, we have prime numbers. Dedekind mimics prime numbers by prime ideals in his algebraic structure. In integers, we have prime factorization. Dedekind mimics it by unique factorization. Fermat's last theorem was proved in 1995. During Kronecker's time, there was a promising proof by Kumar. Dedekind proved that the Kumar's proof holds if and only if the algebraic ring is a unique factorization domain. And then he could show that there are algebraic rings which are not unique factorization domain, and thus fizzled out a promising proof of Fermat's theorem about 100 years ago. From integers, we go to algebraic ring, from God to man. This is to prove theorems about God's creations. I attribute this slide to Paul Erdos, whom I met in my advisor's house. Erdos advised me, God has a book of mathematics. We must seek to prove theorems in his book. Erdos is an atheist. I think what he was trying to tell me is that life is short. there are elegant theorems and we must focus on elegant theorems. From God, we go to man's creation from integers to algebraic ring. This is to prove theorems about God's creation. Now we will go from man to artificial. This is to prove theorems about man's creation. Software is artificial. So we will create something to prove theorems about software. We will go from the algebraic ring to another ring that I am simply going to call a ring R. This is to prove theorems about software. In going from integers to algebraic ring, we lose prime factorization. In going from algebraic ring to R, we will lose commutativity.